This video is on enthalpy changes of combustion. So what I'm going to be talking about in this video is how heat changes in a reaction when we're talking about a combustion reaction. So symbol for this we have to be aware of, and we should be familiar with some of this, is when you're going to have this enthalpy change of combustion, that's going to be a delta H, right? That's our enthalpy. You're typically, or lots of times you might see like the standard state, little, I call it a knot up here, this little, it's like a degree, standard state. The H, right, is the enthalpy. And you might see a little C here, which stands for combustion. And remember that a combustion is any reaction with O2. So anytime you have a reactant, some sort of fuel plus oxygen. If it's a fuel like a hydrocarbon, so C and H, or like an alcohol, so a hydrocarbon with a hydroxide at the end, you are going to get carbon dioxide and water if it's complete combustion. If it's incomplete combustion, you're going to get carbon monoxide and water. So the enthalpy change for the complete combustion of 1 mole of a substance in its standard state in excess oxygen under standard conditions. That's what we talk about when we say standard enthalpy change. So what we're looking at here is a reaction where we're heating water. So you can see they've got the water in the container, some sort of, it's probably a metal container. That's called a calorimeter right here. So here's this, calorimeter. So this is some sort of insulated container. You've got your burner underneath. So like this is like an alcohol burner. This has ethanol. So that's your C2H5OH. As your fuel, this could be like a Bunsen burner also. Any sort of kind of heat source where the combustion's actually happening. And you've got kind of an insulated situation here with the shield and the card on top. And we've got our thermometer and our water to measure the temperature change. So what we need to really think about is what's happening here. And what's happening is that this right here, this burner, this is our reaction. This is where the reaction's happening. And the heat is going into, I'm going to think of this as like our system. So the water, so maybe it's better if I just write water. And the heat's going from the reaction into the water. So what I want you to think about is as the heat leaves the reaction is exothermic. So this is negative, and it's going into the water, which is making it endothermic, which is making that positive. So how can we relate these two to each other? Well, remember Q is heat, and that's going to be in like joules or kilojoules, depending on how big the number is. And delta H is our enthalpy, which is going to be heat per mole. So this is going to be like joules or kilojoules per mole. So it's really just, is it just heat are we talking, or is it heat per mole? So when we talk about our delta H of our reaction, okay, which is combustion in this case, we're looking at the fact that it's going to be a negative Q. It's going to be the opposite of the water. That doesn't mean the Q from the water is negative. It just means it's the opposite sign, right? Because I wrote delta H as positive. And that it's going to be divided by my moles from my reaction. So how much is actually being combusted? So you're going to end up with, right, Q is the mass of the water times the change in temperature of the water and the specific heat of water, all over our moles of reaction. All right, so this is actually very similar, or just like the specific heat lab that you did, or will do if you haven't yet. All right, so let's do a problem, so hopefully I can explain this a little better. So it says using the following experimental data to determine the enthalpy change of combustion of ethanol, given that the specific heat capacity of water is 4.18 joules per gram degree Celsius. All right, so I have right here, here's my CP of water. I'm trying to find this. So my delta H of combustion, right? That is my reaction. So that's what I'm trying to find. And I've got the mass of my water. I've got initial and final temperature of water, so we can find our change in temperature of the water. If I subtract these two, right, my delta T would be 26.2. And then, so that's the water. And then I have the burner, the initial and final mass. So think about what's happening here. This fuel in here, this ethanol, is burning. So the mass is going down. So if I've got the whole burner with the fuel before I burn it, and then the whole burner afterwards, you can see that it's less. So how much fuel did I actually burn? Well, if I subtract these two, I get 1.05 grams of our ethanol. All right, so what do we do with all this? Well, our delta H of our reaction or our combustion, we need to know this Q for the water, and then we need to know how many moles of whatever was our fuel reacted. So let's do these separately maybe. You could do this in one problem as well if you'd like. So Q of the water is going to be the mass of the water, so 150.00 grams, times my change in temperature of the water, 26.2 degrees Celsius, and my specific heat of water, 4.18 joule per gram degrees Celsius. So I multiply all of these, I get, with 3 sig digs because of the temperature, 164,000 joules. And I'm going to convert that to kilojoules. It doesn't say I have to, but that's a pretty large number, and it'd be a lot easier if I just looked at this as 16.4 kilojoules. All right, so we've got the top value. Now we need to find the moles. So the moles of our ethanol is going to be 1.05 grams. And we're going to convert grams to moles. So molar mass, I add up carbon, 2 carbons, 6 hydrogens, 1 oxygen, and I get 46.08 grams. So those divide out. This gives me 0.0228 moles. All right, so my delta H of combustion is going to be negative 16.4 kilojoules all over 0.0228 moles. And this will give me, let's see, negative 719 kilojoules per mole. So that means for each mole of ethanol, this is how much heat will be lost. That's how much heat it will put into the water. Now, if you can look up this value actually. This is like where if I go back to the beginning, we're talking about these standards. Standards, we can look them up. So what is it actually for ethanol? So right here, here's our literature value, meaning like I looked it up on a data table. This is how much heat ethanol should lose as it combusts. All right, so that's a little different from our number. So the real question is why? So this is like an evaluation part of your lab. So possible things when we have combustion reactions like this. So heat lost to the surroundings, meaning all of the heat that the ethanol is losing, as giving off, I should say, it's not all going into the water. Some of it's going into the can and the air around it. If I go back up to this diagram, yeah, the heat's going into here, but some of it's also just going into the air out here or into the container right there, the metal container. So when we look at the temperature of the water increasing, well, some of the other things are increasing their temperature as well, and that wasn't factored into the total heat. So how could that be improved? Well, you'd have to factor in those specific heats for your can and possibly the air into your calculations. So you'd be adding those to the heat. All right, another possible reason this is different is ethanol might not be it might not be burning hot enough. It might not be burning with enough oxygen. Incomplete combustion means not enough O2. So, and you could tell that by getting soot coming out of your flame or a yellow-orange flame. So it's not as efficient. So a way to fix this would be to use what we call a bomb calorimeter. And there's a picture right over here. And you might want to draw this or something similar to it, kind of a sketch of it in your notes. But really what the takeaway from this is much more insulated. So and it's much more contained and close together. So there's very little air or anything else where the heat can escape to or go into. So we're getting just the right amount of oxygen and everything for our reaction to be complete.